Okay, so today it's mostly going to be, it's probably going to be just 30 minutes of me trying to get these to work, because I believe last time I just got stuck with just the way this is, it's the indentation. Oh. Why? Yeah, that's it. It's just a stupid, why there's this fucking space in here. So, let me just, well, okay, that seems to be all fine. If I run this, does it break? Yes, it breaks. Oh, is it like that? Softmax doesn't exist? Softmax. Cool. Okay. So I might just have to add these, and from SciPy, and then basically softmax. SciPy. Do I need to install SciPy? I thought these things were installed automatically. SciPy. Can I just npm it? Can I just npm SciPy? npm pip install SciPy. Oh, it's the shell, not the console. SciPy. So let's remember, we were doing these. So we were doing these projections to Q, K, and V. You know, V was not really needed. Oh, it's actually not. So can it run? So access don't match array. Where? Transpose. There's something off with the shapes. Okay, so dot product attention was calculating both the was returning both the output, but of applying the attention weights to V, but it also was returning the attention weights. Remember, the attention weights were sort of the relationship between the different words. Looking at the projections. So a scaled attention has the wrong shape for transposing operation. The dot product attention method call returns a 3D tensor with shape numheads, max length, and depth. The concatenation of the numheads dimension with max length batch size. No, we don't want the batch size. Maybe we should introduce the batch size now. So where is the problem happening? The problem is happening in scaled attention. scaled attention. So I think scaled attention, yeah, of course. Why are we transposing it? Yeah, that's definitely wrong. 0, 2, 1, 3. So this is definitely wrong. This should be just 3. You know, this is going to be definitely wrong. That's not the kind of transpose that we want to do. But let's see if that at least actually does it work. And now the reshape is not working. So what are we trying to get at? That's the point. So we have, so let's remember, we have our attention weights. They're both like D model, right? So if I do print scale attention shape and print attention weight shape. If I do these, why 1515? Oh yeah, because the attention weights. Okay, something's wrong here. So first what we're doing is we have the in the dot product we have QKV normalization. What is this? Y minus 1. Axis non. So if examples axis 0 along the first axis, y minus 1, it's along the last axis. Okay, so first of all, let's just, so scores is, it takes Q dot product attention. So what is dot product attention? So here we have it's QKV, right? So QKV are basically as just we're giving it XXX. So we're giving it our input. We're giving it our input ID. Now these our input tensor. So this input tensor is let's remember. Before we split the heads, it's got this form, 15 by 10, exactly, 15 by 10. And that's what we want to recover at the end of everything. We want to recover this shape. That's all we have to do. 15, 10. So 15 watts and 10 dimensionalities. The first thing we do is we basically split that into, you know, Q shape. So first Q here, basically we split the heads, and so what we're doing is splitting the heads is adding this dimension here. So we split this like that. So we're essentially saying now we have the first, and this is doing in here in split heads. We're reshaping. So we're saying we're working just with one sentence in only that. So we're we're reshaping X, and length of X, Y. Where we're reshaping it. Length of X. Yeah, length of X is the 15 words. The 15 words. The 15 words. The 15 words. Then the. Yeah, because we have these. I remember I was going to. So we have the 15 words. So we're saying. We're reshaping it to just say. Show me this was complicated, damn it, this was complicated. So this was show me the 15 words but split them in two heads. Of the same depth, because what we wanted is we wanted to have, essentially you want to have at the end here, you want to then transpose, right? Because you want to have two heads, and each head you want to have. So for each head, you want to have 15, basically the 15 words. But then you want to have depth, and depth is basically 5. Why? I'm not gonna go into this right now. I remember. I think I worked through these and it was okay. So this is what gives us these basically matrices of 2, 15, 5. So we're saying for each 2 heads, then we have the 15 words and the 5 dimensions, right? Because we want to have the first 5 and the second 5, just 2 heads, right? This is what splitting is doing. Now, we have this split and we do the dot product attention. Why is this returning it as? So the scaled attention makes sense. It's the same shape as V, because it's V multiplied by the attention weights. But the attention weights is 2 heads. But then it's 15 by 15, which also makes sense because you essentially we have 15 words and 15 words, and so. No, what doesn't make sense is these shouldn't have the heads in here, right? So the attention weights. Now, how the attention weights calculated? Scores axis -1. Scores. Scores is the transpose of. We take Q. Take K. We transpose it. And we'll multiply it. So let us ask ghostwriter. So quick question. What should be the dimensionality of the attention weights? Tensor shape. Num heads max len. Okay, yes, num heads, it also makes sense, yes, because for each, yeah, no, that makes sense, because for each num head, essentially you have 15 words, but you're just comparing the 5 depth, right? So you're just comparing the 5 depth. It just gives you a number because it's like, it's a, yeah. So that's not actually makes sense. That's correct. Max len. So applied the weights to B. So why are we doing so? Why are we normalizing it like this? The axis minus r against the axis along which to normalize the scores. In this case, the scores are normalized across the last dimension. The key sequence. I'm not so sure I understand that. So. But okay. At least let's see if we can get it to work. I mean, it kind of makes sense. So far, it's fine. I think the way this is returned is correct. So scale attention has the same shape and attention weight is the same shape. Now, what we want to do is, what do we want to do? Now we want to concatenate these things again. So what is it? So after we have attention weights and scaled attention, what is it that we want to concatenate? So after we have these, what is it that we want to concatenate? I guess we want to concatenate the 2 dimensions, the heads again, right? So we want to again reshape. So what we want to do is we want to take a look at scaled attention. So we reshape scaled attention of the shape num heads max length depth per head. But that already has it, right? So yes, that already has it. So scaled attention, but dot product attention already gives. Okay, so we reshape scaled attention to have the shape back size, which we know number of heads, max length, depth per head. But dot product so is currently already giving it out in this shape. So we need to exactly that's my point. So we have it already in that shape. Applying the weights. Still doing transpose. No, but the skeleton tensor. That's nice. Num heads using. Fine, but then we need to make a. So we need to make a. So this is not needed. But then we need to concat. So we need to actually go back to the. We need to reshape definitely. So we need to reshape it back to the scaled attention, and we need to reshape it back to max length. In it, what do we have? Length of x, that's what we don't have. Depth, d model. Oh, d model times num heads. That's what we need to have. D model, no, we need to have. So what we need the shape. So we basically need these to be. We need it back to be 1510. So we need to just basically 15, which is max length, which is basically saying how do we do this? So how is it here? Done. Q shape 0, what the hell? Is Q shape or V shape 2? This is what we need. We need V shape 1 because we need the 15, and then essentially we need or even scale to tension. I think I can just use scale tension shape 1, and then we need scale to can you do it like that? Scale tension 0 times scale to tension 2. Does this work like this? So this could actually work, because then what we have here is what we want to check is of concat attention shape. Okay, and then there's this dense multiplication. Then let's just let's see if that works at least. Yay, that works. Awesome. That works. Whether it's correct the way it's done. Like how's reshaping even work? Like how does the I'd like to know more about how the reshape, like is this, how does it know where to, how does it know, and how does it know how to do this? I'm not feeling super confident about what it is that it's actually doing, but I think that's fine. And then we're doing a matrix multiplication of these dens, and that's you know, the other stuff that's going to be learning, and essentially we're returning these two things. So this seems to be okay. Seems to be cool. But what do we have now? So essentially what we now have is the following. So that's, I guess, what we have, isn't it? Prints. Do we have prints in here that we can get rid of input tokens? Maybe let's just do these. I don't think this is needed. The zero is needed. I think that's what we need to do, is these, and then run it. And what we have is the following. We have our input tokens, and then we have our attention weights. Because it's funny, because there's a lot of zeros at the beginning, but then there's something happening, really. Very interesting. After multi-head attention, we just have, yeah, something. We have something. So how can we do anything with it? After the multi-head attention, so that's the actual output. Well, nothing, right? I mean, that essentially is kind of telling you that you know, this was our initial representation, and we've now transformed it into a representation that is this one, that it includes a basically, for example, if we compare example, compare sort of, let's say the word the, right? So the first token, compare tokens after before after multi-head attention. So before is print input IDs 0, and then it's print output 0, I think, right? So I think we don't need to print these things because they're too big. We don't want to print the IDs either. So I can go to this. So essentially we have now basically that kind of information, right? So we have these, which is, and there was another div, right? So it's 0, 1, 2, 3, 4, 5, 6. So if we do 6, or if we compare the output 6, assuming that is correctly done, it's interesting to see that they're quite different, right? Because my theory would be, of course, these, the information that is there and these there are totally different, right? Like position wise, then also the connection of sort of the words around it and stuff like that is different. That is my attention, but I that's my what I'm thinking, right? But I'm not entirely sure how to validate that. So let me ask Ghostwriter, how can we the outcome of all these multi-head attention mechanism is really working well as expected? What are the methods to validate this, right? So we can also compare the input sequences with the output sequence representations. Yeah, okay. By inspecting the attention weights matrix and output representation, we can see which tokens in the input sentence sequence are most important for creating the output sequence. I'm not so sure I understand, but I think that is going to be the next one. So at least we got it to work. And now the next step will be to actually interpret the results and see if there's a way that we can, how can we test that it is doing something roughly okay. From an encoding perspective, right? So whether the encoding it's intuitively okay, or whether there's some kind of mathematical mistake somewhere there. Thank you, and have a good weekend, people.